Okay, everyone, thank you for coming. For the first talk of this afternoon session, we've got Peixue Wu, who's going to be telling us about lower bounds for simulations and open quantum systems.
Okay. Hello, everyone. Today, my talk is about simulation of open quantum system. I don't know why this is not playing. So our main contribution is that we find the lower bound for the simulation cost of open quantum system. Okay. First, you may ask why we care about open quantum system. Okay. So there are two obvious reasons for you to be interested in. First of all, open quantum system is an idealized model that can accurately capture the behavior when your system is interacting with the environment. Second, you can use the open quantum system to design a quantum algorithm. For example, you can design an open quantum system to prepare deep state or ground state in a more efficient way. To talk about the simulation of open quantum system, we recall the so-called strong quantum church theory thesis. Should I wait for that? Okay. So there's only one screen working now. Yeah, sorry for that. The strong church theory thesis says that every quantum mechanical computational process can be simulated using circuit model in an efficient way. Okay. And the simulation of open quantum system is kind of a part of the ultimate goal of the quantum church theory thesis. And the model of the open quantum system is given by the Lindbladian generator. And what you do here is that you take exponential of time times this generator, and this gives you a family of channel that satisfies the semi-group property. And our goal today is that we have access to a unitary gates, and we ask what is the minimal number required to approximate an open system at the target time. Okay, this is what we are going to talk about today. And let's briefly talk about what is the typical method to simulate open quantum system. And so the key idea is that we try to emulate the Stein spring dilation of a quantum channel. And for the Stein spring dilation, we mainly have three ingredients. Usually we have an environment, that is a system interacting with your actual system. And you want to encode your quantum information to a larger system, and also you have your decoding procedure. And in this scenario, it's very simple. The encoding is just by adding some zeros on the environment system, and for the decoding, you just discard your environment system. And now let's rigorously define the simulation cost we are going to talk about today. So we have an accessible unitary set, and we have a family of channel that models the open system, and we want to approximate within error. And the simulation cost is defined as the minimal number of gates to approximate that. And the gates are from your given accessible unitary sets. And the key part is that we allow reset during each during each circuit. Okay. We allow that. Sometimes you can also do mid-circuit measurements to further reduce your simulation cost, but that is not our main goal today. Okay, so this is the simulation cost. And the first question is, this simulation cost is a quantity that is usually non-convex. Okay. So it's really hard to deal with in theory. And the key argument in our work is the following two-step relaxation. Okay. So the first step is that we use randomization idea to introduce the so-called convexified simulation cost. Okay. And the second step is we lower bound the convexified simulation cost using the so-called quantum transportation cost. So this is our hierarchy. And what we do today is we find explicit expression for the quantum transportation cost. Okay. And let's first briefly review what is the so-called convexified simulation cost. So the only difference is that we replace all the gates by random gates. Okay. And we approximate the target open system in an average sense. So we take a mixture of unitaries, and the distance is still smaller than a certain error threshold. And in fact, this randomization can reduce the simulation cost. Okay? And this gives you a lower bound for the deterministic simulation cost. And you can check the following references for how they achieve this reduction by randomization. And also, the convexified simulation cost is easier to handle. And this one naturally induces a transportation cost, which is the central topic for our talk today. Okay, now let's talk about the central part of the talk. That is the quantum transportation cost. Okay, the natural question is, given any two states, rho and sigma, how much does it cost to transport from rho to sigma with limited resources? Okay. And mathematically, you may ask, what is the natural definition of quantum distance between states that can effectively quantify this cost? Okay. And as mentioned in this following paper, the trace distance is actually not a good choice because it is too rough to be correctly capture this behavior. And to fix this issue, what we use is that we generalize this dual picture. Okay. And what we have here is a new constant. That one can encode your transportation information. Okay. And how to define this this new constant is the tricky part of this whole field. And here I introduce a notation called S, and let me explain what is S. So S is actually the generating set of your accessible unitary. Okay. The reason why we want a generating set is that your accessible unitary can be infinite. Okay. For example, when you try to simulate the simple amplitude damping noise, which is a non-unitary noise, what you can do is that you calculate the Stein spring dilation explicitly. Okay? And this gives you two Hamiltonian simulations. And in fact, what you find is that the time is not the usual time you have. So you have a time change. So in order to simulate this open system, what you usually assume is that you have Hamiltonian simulation within a time interval. Okay? And you take your Hamiltonians to be your generating set. That's our typical choice. And given the generating set S, we can define the so-called Lipschitz constant of the observable. Okay? And it's actually given by the operator norm of the commutator. Okay? And actually, this idea was already there. It originates from actually Alan Cohen in the 80s, and Rayful generalizes to the quantum setting. And recently, Li Gao and Cambis Huzay generalizes to the most general setting, and they talk about several properties for this quantum transportation metric. First, you may ask, why do we care about this Lipschitz seminorm? Why do we choose this Lipschitz seminorm? Suppose we have a generating set, okay? There are a set of Hamiltonians, and you take the derivative, type derivative of the observables, evolution of observables. So what you find is that the Lipschitz constant is actually the maximal rate of change for the observable under the dynamics generated by the Hamiltonians. And in this setting, what we have is the accessible unitaries. And if your time interval, okay, is bounded, for example, is O1 order, the circuit, the number of the gates is approximately the Hamiltonian simulation time. Okay? Usually the most expensive part of the simulation business. Okay, finally, we are going to talk about the definition. So definition is the quantum transportation cost for quantum channels. Okay. Suppose we are given a quantum channel, which is usually non-unitary. And we aim to introduce a quantity that can quantify the effort to transform arbitrary states from the input to the output state, okay, evolved by the quantum channel. And in the Heisenberg picture is actually the maximal change of the observables under the observable evolution. So in the picture, imagine we have a non-unitary channel, and we want to use unitary simulations, given by S, and that is the transportation cost. Okay. And the intuition is that if your channel is close to identity, then you have low cost. And if it is far away from the identity, it usually has high cost. And this finally gives you the definition of quantum transportation cost. Recall that the WS is the quantum transportation metric. And here what we have is we have an ancillus, and we have to limit our resource given by the set S, which is a set of operators on a joint system. And this one was already discussed before, but here we take into account the environment-assisted effect. Okay. And more generally, you can choose some other encoding and decoding procedures. For example, you can choose some error correction way to generalize this framework. But our framework mainly talk about the simple encoding by adding zeros and simple decoding by discard the environment. But it can be, it can work for general setting. Okay, and our main theorem is given as follows. So recall that our simulation method is that we simulate our system at a small time, okay, which we call delta t. And we want to simulate the target time capital T. And what we do is that we iterate our quantum circuits. Okay? And that is our total cost. And our bound is for small time t, okay, for small time. And our assumption is that for each accessible unitary, we have a uniformly bounded transportation cost. Second, we have to assume that our open system is ergodic with a unique fixed point. And that is the usual setting. And then our lower bounds behaves like this. It's linear in the time t, and it's given by a ratio of transportation cost of the replacer channel, because we are trying to prepare the state sigma. So eventually we are preparing the replacer channel. Okay, so it's given by the transportation cost of the replacer channel, divided by the transportation mixing time. Okay, and here, this part is, roughly speaking, the transportation cost of your system. And I want to talk a little bit more about the new lower bound we propose, and we want to give you more physical meaning on it. So this lower bound has linear in time t structure, and for the ratio, the upper bound is the true transportation cost of your limit behavior. It's the replacer channel by sigma. And for the denominator, you have two terms. The first one is the maximal transportation cost per unitary. That comes from the choice of your generating set S. You can choose different S, you can have different Ds, but as long as the D is uniformly bounded, this one does not affect your order. And also we have this transportation mixing time. Okay, transportation mixing time. A naive question is how to give an upper bound for this. Okay, and this quick answer is that the usual mixing time is always an upper bound. Okay. But can we do better? And in fact, we can do much better by talking about the exponential decay for transportation metric. And if we have exponential decay for the transportation metric, we have two implications for this strong assumption. We can have a sharp upper bound for usual mixing time, and also we can have a upper bound for the transportation mixing time. Okay. And as you can see, okay, as you can see, in the upper bound for the usual mixing time, you have another dimension factor. So that is usually large. It's a dimension factor. And recently, these two papers used this powerful tool to show some rapid mixing for some open quantum system. But that is I think that is the right way to show the mixing time upper bound. And finally, I want to discuss the key ideas of the main result. Okay, and as we mentioned in our subtitle, our approach is called the Lipschitz continuity approach. And this is the key part of our result, because this basically shows that the transportation cost of the system is lower bound, is a lower bound for the simulation cost of the system. And then by some elementary analysis and semi-group property, you can transform the information at time t to the large time. And then we transfer back, you get the transportation mixing time as a penalty. And finally, I want to discuss a little bit about the summary and also the outlook. Okay. First, we build a lower bound framework for any open quantum system. Okay. But we assume ergodic. It's actually true for non-ergodic case. But in fact, in reality, people don't really care about non-ergodic open system. And we also introduced a convex quantity called quantum transportation cost. And this cost is a key rule. Okay. In fact, we don't have a systematic way of how to efficiently compute this quantum transportation cost. The only advantage over the simulation cost is that we have an explicit formula for this cost. But you really have to pick some clever choice. We call that it's a supremum over a function. You have to choose a clever maximizer to find a good approximation of this transportation cost. And if you're interested, you can see our paper for the details of how to choose that clever states. And in the meantime, our ongoing work can adapt this framework or generalize this framework to provide lower bound on the circuit, on the depth of the circuit rather than the volume. Okay. And also, there are some ongoing work about how to calculate the quantum transportation cost in the many-body system case. Okay. I think that's all I want to talk, and I'm happy to answer any questions.
Thank you. Very nice talk. I was just wondering, you're saying for the transportation cost, you're saying you're trying to transfer from rho to sigma.
Yeah.
I was just wondering what's the similarity and differences between your method and adversary method.
What method?
Quantum adversary method for lower bound. Yeah.
Adversary method? I think quantum adversary method does not apply to open quantum system setting.
Okay.
Because this one is usually irreversible, and I don't know, people didn't try that.
Okay.
Do you have any reference about that?
No, I'm just, it just seems like their structure looks similar. I was just saying if you have any ideas about that.
I think that's more like a problem-specific setting. So it's not. It doesn't work for all the models, and
Okay.
and here I think the transportation cost is something like a strictly weaker lower bound, so that can work for all the possible systems. Yeah.
Okay.
Yeah. So we achieve generality using this transportation cost. Yeah. Yeah.
Okay,
But
that makes
and
sense.
it does have some saturate lower bound in some cases.
What do you mean by saturate lower bound?
Saturate, I mean, we can construct a reasonable upper bound, and upper bound and lower bound can coincide. Yeah, sometimes. Yeah.
Makes sense. Thank you.
Thank you.
Can you say a little bit more? At the end, you said people don't care about non-ergodic systems.
Oh, a little bit.
Can you
Because
elaborate on that?
I try to sell this non-ergodic semigroup to others, and people don't care. That's, yeah, sure.
Yeah. Well,
Yeah.
can you maybe speculate about the prospects of doing this for non-ergodic systems?
Non-ergodic system, for example, I think if you are given any open quantum system, usually it can be non-ergodic. It will converge to a projection onto a subspace. And that part is the what usually we call this the conditional expectation. I would say this. In the QIP, there are some interesting talk in information theory using that idea to transform quantum information more reliably. It can help you design more efficient quantum error correcting codes sometimes. Yeah.
Interesting. I actually already think they're interesting.
Okay. Okay.
So
good,
what I'm
thanks.
wondering
Yeah.
about is like, is there? So I think you're assuming ergodic systems because they're in some sense generic,
Oh,
and
I
your
get- okay,
framework
okay, okay.
applies to that case.
Yes.
But what
thanks.
might
Yeah.
you? Okay.
I
you know, show
understand,
of
yeah.
hands. Who thinks non-ergodic things are interesting? You know? Yeah. All right.
Yeah.
2, 3 people. See.
I-
So you have
yes.
a wide audience of people.
Yeah.
But
Uh,
no, I mean systems with symmetries
Yes.
are non-ergodic, and so I'm just wondering if your framework can be applied in that context.
Yes. Yeah, actually, I think I understand your question better now. I think the question, the reason why I only focus on ergodic case in this talk is that if you design an open quantum system, your goal is try to prepare a state, deep state or ground state. And in that case, you want to design an ergodic system. That's their goal. And you can have different quantum tasks. So in this scenario, we only focus on ergodic case. And because we assume ergodicity, our technical part is much lighter, and it's really easy to write down. Okay. If you see the paper, there are some technical stuff, and that is also true for non-ergodic case. Okay. So in our paper, we assume any non-ergodic setting.
Okay, thanks.
Just a basic question. You said earlier that quantum channel is nonlinear. Does that because you include measurement, or there's something else make it nonlinear?
Sorry, could you repeat which part is linear?
So you said the quantum channel is not linear,
Quantum channel is
and
non.
you assume that it's nonlinear, and that's why you try to do your work.
No,
like one of the
I assume
earliest slides.
non-unitary. I don't know. Quantum channel is always a linear map, right?
Yes, so that's my question. You said nonlinear. So
Oh, maybe I say something wrong. Sorry for that. I mean non-unitary.
non-unitary.
Yeah, non-unitary channels.
Okay,
Yeah.
right.
So we need a true environment to simulate that. Thanks. Yeah.
So for your very first diagram for the quantum circuit, usually for a Lindbladian environment, is the Markovian property is due to that the environment is very large, but in your circuit, it's like there seems to be very few
Yes. a few-
qubits, and then you manually discard the information. Could you explain to what extent the two different situations are equivalent to each other?
Okay, so if you say your environment is large, meaning that you have very complicated interactions with the environment. So that means you have many numbers of the jump operator. Yeah. But sometimes your Lindbladian generator can have less jump operators. then you need less ancilla qubits or environment qubits to do this simulation. Yeah. So yeah.
Even if the environment is large, your jump operator can still be as simple as sigma minus or sigma plus.
I agree. Yeah, but I would say this: the environment size is related to your the number of your jump operators. Mm-hmm. Okay. Yes, and okay, I would say this: if we have less environment qubits, and usually the cost is less. Okay. So we usually want to find a simulation protocol that has less environment qubits. Yeah. Yeah, we can talk about this later. Yeah.
We have a couple of minutes break now for people to move around before the next talk.